For Lab 1, titled Constant Velocity, I observed the motion of a lacrosse ball. The objective of this lab was to understand and predict the motion under Newton's second law and under the assumption of zero net forces acting on the system. By Newton's second law, a system under zero net forces will experience constant velocity. Using Newton's second law, I was able to build a computational model to predict this motion of the ball. Following a comparison of the predicted motion and the observed motion of the ball, I found that my predictions and observations were in agreement. The specific situation being observed was the motion of a lacrosse ball across an assumed horizontal flat surface. Once this motion was captured with my cell phone, the video was input into the tracker program and the position and time data points were extracted from the frames of the lacrosse ball's motion. In Tracker, I had to align the axes with the motion of the ball. The motion of the ball is in the positive x direction, and the origin is aligned with the initial position of the ball in the video. If I had chosen to flip the axes, the ball's motion would be in the negative x direction. Since velocity is a vector quantity, the direction of the velocity determined would change, but the magnitude would remain the same. Next, I had to choose the portion of the video I wanted to analyze, which was following the lacrosse ball. Finally, I calibrated the program, and I did this with a standard ruler, as pictured in the video. The data points extracted from the video constituted the observed position data of the motion of the ball. The program also output a graph of the position and time of the lacrosse ball over the 0.7-second time interval, which displayed an approximately linear graph as expected for constant velocity motion. We can also predict the motion of the lacrosse ball under the same initial conditions presumed for the tracker video using a computational model. The predicted motion of the ball from the computational model uses the fundamental principle of Newton's second law. Under Newton's second law, the final velocity of the object's motion is equal to the object's initial velocity when the sum of all forces acting on the system are equal to zero. This principle was used in writing the code to model the ball's motion. Before the code could be run, the initial conditions of the system had to be updated. The mass of the lacrosse ball, its initial position vector, and initial velocity vector were input into the code. The initial velocity of the lacrosse ball was calculated using the data points from Tracker by dividing the difference between the second and initial position of the ball by the time span between these positions. Now, for the code to actually predict the motion of the lacrosse ball under the assumption of zero net forces acting on the system, the assignment statements for the net force, new velocity, and new position were updated according to Newton's second law. So a net force of 0 was input, remembering that Newton's second law states that the final velocity is equal to the initial velocity plus the net force times the time in which the force is acting on the system, all divided by the mass of the object in motion. The equivalent assignment statement for Newton's second law is present here. This allows us to predict the final velocity of the lacrosse ball and thus predict the final position of the ball here using a position update formula. The final velocity of the ball serves as an estimate for the average velocity, and the initial position is known from tracker data. So after inputting these parameters, I ran the code, which produces a graph of the position versus time for the predicted motion of the ball, and a corresponding visual of the ball's motion in the positive x direction. The graph displayed is linear as expected for constant velocity motion. After gathering the predicted and observed position data for the motion of the lacrosse ball, I was able to compare the two graphs for the predicted and observed motion of the ball. Here is a graph of the position versus time for the predicted and observed motion of the ball along the positive x direction. As you can see, the graphs of the predicted and observed motion agree quite well. However, there is a slight disparity in between them towards the end of the ball's motion. The slope of the predicted motion of the ball is less steep than the observed motion of the ball, meaning the ball's observed velocity was somehow faster than its predicted motion data. This difference could possibly be attributed to a slight slope on the floor's surface. In this case, the ball may have sped up due to a slight downward gradient in the floor. So what does this mean? In the system observed, we were able to safely assume that no net forces were acting on the ball during its motion, as indicated by the ball's constant velocity motion and the agreement between the observed motion of the ball and its predicted motion. However, is it possible to say how many pushes and pulls were added together to give the zero net force in the ball's motion? Just from observation, it isn't possible to determine the components of individual forces acting on the ball. All that can be concluded is that the ball's constant velocity motion indicated that zero net forces acted on the ball during its motion. Thank you for watching.